Stegosaurus. Stegosaurus, /STSRS/, from Greek stegos, sigma tau gamma omicron sigma, which means roof, and sauros, sigma alpha rho omicron sigma, which means lizard, is a genus of herbivorous thyreophorian dinosaur. Fossils of this genus date to the late Jurassic period, where they are found in Kimmeridgian to early Tithonian age strata, between 155 and 150 million years ago, in the western United States and Portugal. Of the species that have been classified in the Upper Morrison Formation of the western U.S., only 3 are universally recognized: S. stenops, S. ungulatus and S. sulcatus. The remains of over 80 individual animals of this genus have been found. Stegosaurus would have lived alongside dinosaurs such as Apatosaurus, Diplodocus, Brachiosaurus, Allosaurus, and Ceratosaurus. The latter two may have preyed on it. These were large, heavily built, herbivorous quadrupeds with rounded backs, short forelimbs, long hind limbs, and tails held high in the air. Due to their distinctive combination of broad, upright plates and tail tipped with spikes, Stegosaurus is one of the most recognizable kinds of dinosaurs. The function of this array of plates and spikes has been the subject of much speculation among scientists. Today, it is generally agreed that their spiked tails were most likely used for defense against predators, while their plates may have been used primarily for display, and secondarily for thermal regulatory functions. Stegosaurus had a relatively low brain-to-body mass ratio. It had a short neck and a small head, meaning it most likely ate low-lying bushes and shrubs. One species, Stegosaurus ungulatus, is the largest known of all the stegosaurians, bigger than related dinosaurs such as Cantrosaurus and Huayongasaurus. Stegosaurus remains were first identified during the Bone Wars by Othniel Charles Marsh at Dinosaur Ridge National Landmark. The first known skeletons were fragmentary and the bones were scattered, and it would be many years before the true appearance of these animals, including their posture and plate arrangement, became well understood. Despite its popularity in books and film, mounted skeletons of Stegosaurus did not become a staple of major natural history museums until the mid-20th century, and many museums have had to assemble composite displays from several different specimens due to a lack of complete skeletons. Stegosaurus is one of the better-known dinosaurs, and has been featured in film, postal stamps, and many other types of media. Discovery and history. Stegosaurus, one of the many dinosaurs first collected and described in the Bone Wars, was originally named by Othniel Charles Marsh in 1877, from remains recovered north of Morrison, Colorado. These first bones became the holotype of Stegosaurus armatus. Marsh initially believed the remains were from an aquatic turtle-like animal, and the basis for its scientific name, roof-fed lizard, was due to his early belief that the plates lay flat over the animal's back, overlapping like the shingles, tiles, on a roof. A wealth of Stegosaurus material was recovered over the next few years, and Marsh published several papers on the genus from 1877 to 1897. In 1878, Edward Drinker Cope named Hypserophus discursus as another stegosaurian based on fragmentary fossils from Cope's Quarry 3 near the Cope's Nipple site in Garden Park, Colorado. Many later researchers have considered Hypserophus to be a synonym of Stegosaurus, though Peter Galton, 2010, suggested that it is distinct based on differences in the vertebrae. Marsh named a second species, Stegosaurus ungulatus, in 1879, and finally gave a more detailed description of all the Stegosaurus fossils collected so far the following year. In 1881, he named a third species Stegosaurus affinis, based only on a hip bone. This species is generally agreed to have been inadequately described, and therefore is a nomen nudum, a name lacking a formal description. The specimen was later lost. Marsh continued to collect and examine new Stegosaurus specimens, and in 1887 he named 3 new species, Stegosaurus stenops, S. duplex, and S. sulcatus. Though it had not yet been completely prepared, the nearly complete and articulated type specimen of Stegosaurus stenops allowed Marsh to complete the first attempt at a reconstructed Stegosaurus skeleton. This first reconstruction, of S. ungulatus with missing parts filled in from S. stenops, was published by Marsh in 1891. In 1893, Richard Lydekker mistakenly republished Marsh's drawing under the label Hypserophus. The next species of Stegosaurus to be named was S. marshii, by Frederick Lucas in 1901. Lucas reclassified this species in the new genus Hoplitosaurus later that year. Lucas also re-examined the issue of the life appearance of Stegosaurus, coming to the conclusion that the plates were arranged in pairs in 2 rows along the back, arranged above the bases of the ribs. Lucas commissioned Charles R. Knight to produce a life restoration of S. ungulatus based on his new interpretation. However, the following year, Lucas wrote that he now believed the plates were probably attached in staggered rows. In 1910, Richard Swan Lull wrote that the alternating pattern seen in S. Stenops was probably due to shifting of the skeleton after death. He led the construction of the first ever Stegosaurus skeletal mount at the Peabody Museum of Natural History, which was depicted with paired plates. In 1914, Charles Gilmore argued against Lull's interpretation, noting that several specimens of S. Stenops, including the now completely prepared holotype, preserved the plates in alternating rows near the peak of the back, and that there was no evidence of the plates having shifted relative to the body during fossilization. Gilmore and Lucas' interpretation became the generally accepted standard, and Lull's mount at the Peabody Museum was changed to reflect this in 1924. Sophie the Stegosaurus is the most nearly complete fossil specimen of a Stegosaurus. It is a young adult of undetermined sex, 5.6 meters, 18 feet, long and 2.9 meters, 9.5 feet, tall. The specimen, which was found in Wyoming, is 85% intact, containing 360 bones. It was put on display at the Natural History Museum, London in December 2014. Plate arrangement. One of the major subjects of books and articles about Stegosaurus is the plate arrangement. The argument has been a major one in the history of dinosaur reconstruction. 4 possible plate arrangements have been proposed over the years. Species. Many of the species initially described have since been considered to be invalid or synonymous with earlier named species, leaving 2 well-known and 1 poorly known species. Confirmed Stegosaurus remains have been found in the Morrison Formation stratigraphic zones 2 to 6, with additional remains possibly referable to Stegosaurus recovered from stratigraphic zone 1. Susanna Maidman and colleagues in 2008 proposed extensive alterations to the taxonomy of Stegosaurus. They advocated synonymizing S. stenops and S. ungulatus with S. armatus, and syncing Hesperosaurus and Wuerhosaurus into Stegosaurus, with their type species becoming Stegosaurus mjosi and Stegosaurus homeni, respectively. They regarded S. longispinus as dubious. Thus, their conception of Stegosaurus would include 3 valid species, S. armatus, S. homeni, and S. mjosi, and would range from the late Jurassic of North America and Europe to the early Cretaceous of Asia. However, this classification scheme was not followed by other researchers, and a 2017 cladistic analysis co-authored by Maidman with Thomas Raven rejects the synonymy of Hesperosaurus with Stegosaurus. In 2015, Maidman et al. Revised their suggestion due to the recognition by Galton of S. armatus as a nomen dubium and its replacement by S. stenops as type species. Doubtful species and junior synonyms. Reassigned species. Description. The quadrupedal Stegosaurus is one of the most easily identifiable dinosaur genera, due to the distinctive double row of kite-shaped plates rising vertically along the rounded back and the 2 pairs of long spikes extending horizontally near the end of the tail. Although large individuals could grow up to 9 meters, 29.5 feet, in length and 5.3 to 7 metric tons, 5.8 to 7.7 short tons, in weight, the various species of Stegosaurus were dwarfed by contemporaries, the giant sauropods. Some form of armor appears to have been necessary, as Stegosaurus species coexisted with large predatory theropod dinosaurs, such as Allosaurus and Ceratosaurus. Most of the information known about Stegosaurus comes from the remains of mature animals. More recently, though, juvenile remains of Stegosaurus have been found. One subadult specimen, discovered in 1994 in Wyoming, is 4.6 meters, 15.1 feet, long and 2 meters, 6.6 feet, high, and is estimated to have weighed 2.4 metric tons, 2.6 short tons, while alive. It is on display in the University of Wyoming Geological Museum. Skull. The long and narrow skull was small in proportion to the body. It had a small antorbital fenestra, the hole between the nose and eye common to most archosaurs, including modern birds, though lost in extant crocodilians. The skull's low position suggests that Stegosaurus may have been a browser of low-growing vegetation. This interpretation is supported by the absence of front teeth and their likely replacement by a horny beak or rhamphotheca. The lower jaw had flat downward and upward extensions that would have completely hidden the teeth when viewed from the side, and these probably supported a turtle-like beak in life. The presence of a beak extended along much of the jaws may have precluded the presence of cheeks in these species. Such an extensive beak was probably unique to Stegosaurus and some other advanced stegosaurids among ornithischians, which usually had beaks restricted to the jaw tips. Other researchers have interpreted these ridges as modified versions of similar structures in other ornithischians which might have supported fleshy cheeks, rather than beaks. Stegosaurian teeth were small, triangular, and flat, where facets show that they did grind their food. Despite the animal's overall size, the brain case of Stegosaurus was small, being no larger than that of a dog. A well-preserved Stegosaurus brain case allowed Othniel Charles Marsh to obtain, in the 1880s, a cast of the brain cavity or endocast of the animal, which gave an indication of the brain size. The endocast showed the brain was indeed very small, the smallest proportionally of all dinosaur endocasts then known. The fact that an animal weighing over 4.5 metric tons, 5 short tons, could have a brain of no more than 80 grams, 2.8 ounces, contributed to the popular old idea that all dinosaurs were unintelligent, an idea now largely rejected. Actual brain anatomy in Stegosaurus is poorly known, but the brain itself was small even for a dinosaur, fitting well with a slow, herbivorous lifestyle and limited behavioral complexity. Skeleton. In Stegosaurus DINOSAURS there are 27 bones in the vertebral column anterior to the sacrum, a varying number of vertebrae in the sacrum, with 4 in most subadults, and around 46 caudal, tail, vertebrae. The presacrals are divided into cervical, neck, and dorsal, back, vertebrae, with around 10 cervicals and 17 dorsals, the total number being 1 greater than in Hesperosaurus, 2 greater than Huayongasaurus, although Mural preserves 17 cervicals and an unknown number of dorsals. The first cervical vertebra is the axis bone, which is connected and often fused to the atlas bone. Farther posteriorly, the proportionally larger the cervicals become, although they do not change greatly in anything other than size. Past the first few dorsals, the centrum of the bones become more elongate front to back, and the transverse processes become more elevated dorsal. The sacrum of Stegosaurus includes 4 sacral vertebrae, but one of the dorsals is also incorporated into the structure. In some specimens of Stegosaurus, a caudal is also incorporated, as a caudosacral. In Hesperosaurus there are 2 dorsosacrals, and only 4 fused sacrals, but in Kentrosaurus there may be as many as 7 vertebrae in the sacrum, with both dorsosacrals and caudosacrals. Stegosaurus preserves 46 caudal vertebrae, and up to 49, and along the series both the centrums and the neural spines become smaller, until the neural spines disappear at caudal 35. Around the middle of the tail, the neural spines become bifurcated, meaning they are divided near the top. With multiple well-preserved skeletons, Stegosaurus preserves all regions of the body, including the limbs. The scapula, shoulder blade, is subrectangular, with a robust blade. Though it is not always perfectly preserved, the acromion ridge is slightly larger than in Kentrosaurus. The blade is relatively straight, although it curves towards the back. There is a small bump on the back of the blade, that would have served as the base of the triceps muscle. Articulated with the scapula, the coracoid is subcircular. The hind feet each had 3 short toes, while each forefoot had 5 toes, only the inner 2 toes had a blunt hoof. The phalangeal formula is 2-2-2-2-1, meaning the innermost finger of the forelimb has 2 bones, the next has 2, etc. All forelimbs were supported by pads behind the toes. The forelimbs were much shorter than the stocky hind limbs, which resulted in an unusual posture. The tail appears to have been held well clear of the ground, while the head of Stegosaurus was positioned relatively low down, probably no higher than 1 meter, 3.3 feet, above the ground. Plates. The most recognizable features of Stegosaurus are its dermal plates, which consisted of between 17 and 22 separate plates and flat spines. These were highly modified osteoderms, bony cord scales, similar to those seen in crocodiles and many lizards today. They were not directly attached to the animal's skeleton, instead arising from the skin. The largest plates were found over the hips and could measure over 60 centimeters, 24 in, wide and 60 centimeters, 24 in, tall. In a 2010 review of Stegosaurus species, Peter Galton suggested that the arrangement of the plates on the back may have varied between species, and that the pattern of plates as viewed in profile may have been important for species recognition. Galton noted that the plates in Stegosaurus have been found articulated in 2 staggered rows, rather than paired. Fewer S. ungulatus plates have been found, and none articulated, making the arrangement in this species more difficult to determine. However, the type specimen of S. ungulatus preserves 2 flattened spine-like plates from the tail that are nearly identical in shape and size, but are mirror images of each other, suggesting that at least these were arranged in pairs. Many of the plates are manifestly chiral and no 2 plates of the same size and shape have been found for an individual, however plates have been correlated between individuals. Well-preserved integumentary impressions of the plates of Hesperosaurus show a smooth surface with long and parallel, shallow grooves. This indicates that the plates were covered in keratinous sheaths. Classification. Stegosaurus was the first named genus of the family Stegosauridae. It is the type genus that gives its name to the family. The Stegosauridae are one of two families within the infraorder Stegosauria, with the other being the Huayongasauridae. The infraorder Stegosauria lies within the Thyreophora, or armored dinosaurs, a suborder which also includes the more diverse Ankylosaurs. The stegosaurs were a clade of animals similar in appearance, posture, and shape that mainly differed in their array of spikes and plates. Among the closest relatives to Stegosaurus are Urosaurus from China and Kintrosaurus from East Africa. The following cladogram shows the position of Stegosaurus within the Stegosauridae according to Mateus, 2009. Origin. The origin of Stegosaurus is uncertain, as few remains of basal Stegosaurs and their ancestors are known. Recently, stegosaurids have been shown to be present in the Lower Morrison Formation, existing several million years before the occurrence of Stegosaurus itself, with the discovery of the related Hesperosaurus from the early Cambrian. The earliest stegosaurid, the genus Lexivosaurus, is known from the Oxford Clay Formation of England and France, giving it an age of early to middle Colovian. The earlier and more basal genus Huayongasaurus from the Middle Jurassic of China, some 165 million years ago, Maya, antedates Stegosaurus by 20 million years and is the only genus in the family Huayongasauridae. Earlier still is Celytosaurus, from early Jurassic England, which lived about 190 Maya. It possessed features of both stegosaurs and ankylosaurs. Imosaurus from Germany was another small quadruped, while Scutellosaurus from Arizona was an even earlier genus and was facultatively bipedal. These small, lightly armored dinosaurs were closely related to the direct ancestor of both stegosaurs and ankylosaurs. A trackway of a possible early armored dinosaur, from around 195 Maya, has been found in France. Paleobiology. Posture and movement. Soon after its discovery, Marsh considered Stegosaurus to have been bipedal, due to its short forelimbs. He had changed his mind, however, by 1891, after considering the heavy build of the animal. Although Stegosaurus is undoubtedly now considered to have been quadrupedal, some discussion has occurred over whether it could have reared up on its hind legs, using its tail to form a tripod with its hind limbs, to browse for higher foliage. This has been proposed by Backer and opposed by Carpenter. A study by Mallison, 2010, found support for a rearing up posture in Kentrosaurus, though not for ability for the tail to act as a tripod. Stegosaurus had short forelimbs in relation to its hind limb. Furthermore, within the hind limbs, the lower section, comprising the tibia and fibula, was short compared with the femur. This suggests it could not walk very fast, as the stride of the back legs at speed would have overtaken the front legs, giving a maximum speed of 6 to 7 km per hour, 3.7 to 4.3 miles per hour. Tracks discovered by Matthew Mossbrucker, Morrison Natural History Museum, Colorado, suggest that Stegosaurus lived and traveled in multiple age herds. One group of tracks is interpreted as showing 4 or 5 baby stegosaurs moving in the same direction, while another has a juvenile stegosaur track with an adult track overprinting it. As the plates would have been obstacles during copulation, it is possible the female stegosaur laid on her side as the male mounted her from behind. Another suggestion is that the female would stand on all fours but squat the forelimbs and raise the tail slightly to the side as the male rested its forelimbs on her broad pelvis. However, this would not explain how their reproductive organs can touch, as there is no evidence of muscle attachments for a mobile penis nor a baculum in dinosaurs. Plate function. The function of Stegosaurus plates has been much debated. Marsh suggested that they functioned as some form of armor, though Davitashvili, 1961, disputed this, claiming that they were too fragile and ill-placed for defensive purposes, leaving the animal's sides unprotected. Nevertheless, others have continued to support a defensive function. Backer suggested in 1986 that the plates were covered in horn, comparing the surface of the fossilized plates to the bony cores of horns in other animals known or thought to bear horns. Christensen and Chop, 2010, having studied a well-preserved specimen of Hesperosaurus with skin impressions, concluded that the plates were covered in a keratin sheath which would have strengthened the plate as a whole and provided it with sharp cutting edges. Backer stated that Stegosaurus could flip its osteoderms from one side to another to present a predator with an array of spikes and blades that would impede it from closing sufficiently to attack the Stegosaurus effectively. He contends that they had insufficient width for them to stand erect easily in such a manner as to be useful in display without continuous muscular effort. Mobility of the plates, however, has been disputed by other paleontologists. Another possible function of the plates is they may have helped to control the body temperature of the animal, in a similar way to the sails of the Pelycosaurs Dimetrodon and Edaphosaurus, and modern elephant and rabbit ears. The plates had blood vessels running through grooves, and air flowing around the plates would have cooled the blood. Buffernell, et al. 1986, found extreme vascularization of the outer layer of bone, which was seen as evidence that the plates acted as thermal regulatory devices. Likewise, 2010 structural comparisons of Stegosaurus plates to alligator osteoderms seem to support the conclusion that the potential for a thermal regulatory role in the plates of Stegosaurus definitely exists. The thermoregulation hypothesis has been seriously questioned, since other stegosaurs such as Kentrosaurus had more low surface area spikes than plates, implying that cooling was not important enough to require specialized structural formations such as plates. However, it has also been suggested that the plates could have helped the animal increase heat absorption from the sun. Since a cooling trend occurred towards the end of the Jurassic, a large ectothermic reptile might have used the increased surface area afforded by the plates to absorb radiation from the sun. Christensen and Chop, 2010, state that the presence of a smooth, insulating keratin covering would have hampered thermoregulation, but such a function cannot be entirely ruled out, as extant cattle and ducks use horns and beaks to dump excess heat despite the keratin covering. Histological surveys of plate microstructure attributed the vascularization to the need to transport nutrients for rapid plate growth. The vascular system of the plates have been theorized to have played a role in threat displaying, as Stegosaurus could have pumped blood into them, causing them to blush and give a colorful, red warning. However, Christensen and Chop, 2010, consider this unlikely, as stegosaur plates were covered in horn rather than skin. The plate's large size suggests that they may have served to increase the apparent height of the animal, either to intimidate enemies or to impress other members of the same species in some form of sexual display. A 2015 study of the shapes and sizes of Hesperosaurus plates suggested that they were sexually dimorphic, with wide plates belonging to males and taller plates belonging to females. Christensen and Chop, 2010, proposed that the display function would have been reinforced by the horny sheath, which would have increased the visible surface, and such horn structures are often brightly colored. Some have suggested that plates and stegosaurs were used to allow individuals to identify members of their species. The use of exaggerated structures in dinosaurs as species identification has been questioned, as no such function exists in modern species. Thagomizer, tail spikes. Debate has been going on about whether the tail spikes were used for display only, as posited by Gilmore in 1914, or used as a weapon. Robert Bakker noted the tail was likely to have been much more flexible than that of other dinosaurs, as it lacked ossified tendons, thus lending credence to the idea of the tail as a weapon. However, as Carpenter has noted, the plates overlap so many tail vertebrae, movement would be limited. Bakker also observed that Stegosaurus could have maneuvered its rear easily, by keeping its large hind limbs stationary and pushing off with its very powerfully muscled but short forelimbs, allowing it to swivel deftly to deal with attack. More recently, a study of the tail spikes by McQuinney et al., which showed a high incidence of trauma-related damage, lends more weight to the position that the spikes were indeed used in combat. This study showed that 9.8% of Stegosaurus specimens examined had injuries to their tail spikes. Additional support for this idea was a punctured tail vertebra of an Allosaurus, into which a tail spike fits perfectly. Stenops had 4 dermal spikes, each about 60 to 90 centimeters, 2.0 to 3.0 feet, long. Discoveries of articulated stegosaur armor show, at least in some species, these spikes protruded horizontally from the tail, not vertically as is often depicted. Initially, Marsh described S. ungulatus as having 8 spikes in its tail, unlike S. stenops. However, recent research re-examined this and concluded this species also had 4. Second brain. At one time, stegosaurs were described as having a second brain in their hips. Soon after describing Stegosaurus, Marsh noted a large canal in the hip region of the spinal cord, which could have accommodated a structure up to 20 times larger than the famously small brain. This has led to the influential idea that dinosaurs like Stegosaurus had a second brain in the tail, which may have been responsible for controlling reflexes in the rear portion of the body. This brain was proposed to have given a Stegosaurus a temporary boost when it was under threat from predators. This space, however, is more likely to have served other purposes. The sacrolumbar expansion is not unique to stegosaurs, nor even sauropods. It is also present in birds. In their case, it contains what is called the glycogen body, a structure whose function is not definitely known, but which is postulated to facilitate the supply of glycogen to the animal's nervous system. It also may function as a balance organ, or reservoir of compounds to support the nervous system. Growth. Juveniles of Stegosaurus have been preserved, probably showing the growth of the genus. The 2 juveniles are both relatively small, with the smaller individual being 1.5 meters, 4.9 feet, long, and the larger having a length of 2.6 meters, 8.5 feet. The specimens can be identified as not mature because they lack the fusion of the scapula and coracoid, and the lower hind limbs. Also, the pelvic region of the specimens are similar to Gentrosaurus juveniles. One 2009 study of Stegosaurus specimens of various sizes found that the plates and spikes had delayed histological growth in comparison to the skeleton, and when the dinosaur reached maturity, growth in the osteoderms may have increased. A 2013 study concluded, based on the rapid deposition of highly vascularized fibrolamellar bone, that Gentrosaurus had a quicker growth rate than Stegosaurus, contradicting the general rule that larger dinosaurs grew faster than smaller ones. Diet: Stegosaurus and related genera were herbivores. However, their teeth and jaws are very different from those of other herbivorous ornithischian dinosaurs, suggesting a different feeding strategy that is not yet well understood. The other ornithischians possess teeth capable of grinding plant material and a jaw structure capable of movements in planes other than simply orthal, i.e. not only the fused up-down motion to which stegosaur jaws were likely limited. Unlike the sturdy jaws and grinding teeth common to its fellow ornithischians, Stegosaurus, and all stegosaurians, had small, peg-shaped teeth that have been observed with horizontal wear facets associated with tooth-food contact, and their unusual jaws were probably capable of only orthal, up-down, movements. Their teeth were not tightly pressed together in a block for efficient grinding, and no evidence in the fossil record of stegosaurians indicates use of gastroliths, the stones some dinosaurs, and some present-day bird species, ingested, to aid the grinding process. So how exactly Stegosaurus obtained and processed the amount of plant material required to sustain its size remains poorly understood. The Stegosaurians were widely distributed geographically in the late Jurassic. Paleontologists believe it would have eaten plants such as mosses, ferns, horsetails, cycads, and conifers or fruits. Grazing on grasses, seen in many modern mammalian herbivores, would not have been possible for Stegosaurus, as grasses did not evolve until late into the Cretaceous period, long after Stegosaurus had become extinct. One hypothesized feeding behavior strategy considers them to be low-level browsers, eating low-growing fruit of various non-flowering plants, as well as foliage. This scenario has Stegosaurus foraging at most 1 meter above the ground. Conversely, if Stegosaurus could have raised itself on 2 legs, as suggested by Backer, then it could have browsed on vegetation and fruits quite high up, with adults being able to forage up to 6 meters, 20 feet, above the ground. A detailed computer analysis of the biomechanics of Stegosaurus's feeding behavior was performed in 2010, using 2 different 3-dimensional models of Stegosaurus teeth given realistic physics and properties. Bite force was also calculated using these models and the known skull proportions of the animal, as well as simulated tree branches of different size and hardness. The resultant bite forces calculated for Stegosaurus were 140.1 newtons, N, 183.7 N, and 275 N, for anterior, middle and posterior teeth, respectively, which means its bite force was less than half that of a Labrador retriever. Stegosaurus could have easily bitten through smaller green branches, but would have had difficulty with anything over 12 mm in diameter. Stegosaurus, therefore, probably browsed primarily among smaller twigs and foliage, and would have been unable to handle larger plant parts unless the animal was capable of biting much more efficiently than predicted in this study. However, a 2016 study indicates that Stegosaurus's bite strength was stronger than previously believed. Comparisons were made between it, represented by a specimen known as Sophie from the United Kingdom's Natural History Museum, and 2 other herbivorous dinosaurs, Erlikosaurus and Plateosaurus, to determine if all 3 had similar bite forces and similar niches. Based on the results of the study, it was revealed that Stegosaurus had a bite similar in strength to that of modern herbivorous mammals, in particular, cattle and sheep. Based on this data, it is likely Stegosaurus also ate woodier, tougher plants such as cycads, perhaps even acting as a means of spreading cycad seeds. Paleo Ecology. The Morrison Formation is interpreted as a semi-arid environment with distinct wet and dry seasons, and flat floodplains. Vegetation varied from river-lining forests of conifers, tree ferns, and ferns, gallery forests, to fern savannas with occasional trees such as the araucaria-like conifer brachyphyllum. The flora of the period has been revealed by fossils of green algae, fungi, mosses, horsetails, ferns, cycads, ginkgos, and several families of conifers. Animal fossils discovered include bivalves, snails, ray-finned fishes, frogs, salamanders, turtles like Dorsodactylis, sphenodonts, lizards, terrestrial and aquatic crocodilomorphans like Hoploschius, several species of pterosaurs such as Harpactognathus and Mesodactylus, numerous dinosaur species, and early mammals such as docodonts, like Docodon, multituberculates, symmetrodonts, and triconodonts. Dinosaurs that lived alongside Stegosaurus included Theropods Allosaurus, Saurophaganax, Torvosaurus, Ceratosaurus, Marchosaurus, Stoxosaurus, Ornitholestes, Coelurus, and Tyncolagrius. Sauropods dominated the region, and included Brachiosaurus, Apatosaurus, Diplodocus, Camarasaurus, and Barosaurus. Other ornithischians included Camptosaurus, Gargoyleosaurus, Dryosaurus, Othniellosaurus, and Drinker. Stegosaurus is commonly found at the same sites as Allosaurus, Apatosaurus, Camarasaurus, and Diplodocus. Stegosaurus may have preferred drier settings than these other dinosaurs. In popular culture, one of the most recognizable of all dinosaurs, Stegosaurus has been depicted on film, in cartoons and comics and as children's toys. Due to the fragmentary nature of most early Stegosaurus fossil finds, it took many years before reasonably accurate restorations of this dinosaur could be produced. The earliest popular image of Stegosaurus was an engraving produced by A. Tobin for the November 1884 issue of Scientific American, which included the dinosaur amid a speculative Morrison age landscape. Tobin restored the Stegosaurus as bipedal and long-necked, with the plates arranged along the tail and the back covered in spikes. This covering of spikes might have been based on a misinterpretation of the teeth, which Marsh had noted were oddly shaped, cylindrical, and found scattered, such that he thought they might turn out to be small dermal spines. Marsh published his more accurate skeletal reconstruction of Stegosaurus in 1891, and within a decade Stegosaurus had become among the most illustrated types of dinosaur. Artist Charles R. Knight published his first illustration of Stegosaurus ungulatus based on Marsh's skeletal reconstruction in a November 1897 issue of the Century magazine. This illustration would later go on to form the basis of the stop-motion puppet used in the 1933 film King Kong. Like Marsh's reconstruction, Knight's first restoration had a single row of large plates, though he next used a double row for his more well-known 1901 painting, produced under the direction of Frederick Lucas. Again under Lucas, Knight revised his version of Stegosaurus again 2 years later, producing a model with a staggered double row of plates. Knight would go on to paint a stegosaur with a staggered double-plate row in 1927 for the Field Museum of Natural History, and was followed by Rudolph F. Zallinger, who painted Stegosaurus this way in his Age of Reptiles mural at the Peabody Museum in 1947. Stegosaurus made its major public debut as a papier-mâché model commissioned by the U.S. National Museum of Natural History for the 1904 Louisiana Purchase Exposition. The model was based on Knight's latest miniature with the double row of staggered plates, and was exhibited in the United States Government Building at the Exposition in St. Louis before being relocated to Portland, Oregon for the Lewis and Clark Centennial Exposition in 1905. The model was moved to the Smithsonian National Museum of Natural History, now the Arts and Industries Building, in Washington, D.C., along with other prehistory displays, and to the current National Museum of Natural History building in 1911. Following renovations to the museum in the 2010s, the model was moved once again for display at the Museum of the Earth in Ithaca, New York. The popularity of Stegosaurus is owed partly to its prominent display in natural history museums. Though considered one of the most distinctive types of dinosaur, Stegosaurus displays were missing from a majority of museums during the first half of the 20th century, due largely to the disarticulated nature of most fossil specimens. Until 1918, the only mounted skeleton of Stegosaurus in the world was O.C. Marsh's type specimen of S. ungulatus at the Peabody Museum of Natural History, which was put on display in 1910. However, this mount was dismantled in 1917 when the old Peabody Museum building was demolished. This historically significant specimen was remounted ahead of the opening of the new Peabody Museum building in 1925. 1918 saw the completion of the second Stegosaurus mount, and the first depicting S. stenops. This mount was created under the direction of Charles Gilmore at the U.S. National Museum of Natural History. It was a composite of several skeletons, primarily USNM 6531, with proportions designed to closely follow the S. stenops type specimen, which had been on display in relief nearby since 1918. The aging mount was dismantled in 2003 and replaced with a cast in an updated pose in 2004. A third mounted skeleton of Stegosaurus, referred to as stenops, was put on display at the American Museum of Natural History in 1932. Mounted under the direction of Charles J. Long, The American Museum mount was a composite consisting of partial remains filled in with replicas based on other specimens. In his article about the new mount for the museum's journal, Barnum Brown described, and disputed, the popular misconception that the Stegosaurus had a second brain in its hips. Another composite mount, using specimens referred to as ungulatus collected from Dinosaur National Monument between 1920 and 1922, was put on display at the Carnegie Museum of Natural History in 1940.